Brilliant. Let's move this slightly over here. So I'm not going to read all of this, but you've got regenerative braking, where the energy comes back in to the system from the braking, and then you got maximum energy transfer 60% of underline, because that comes into account there. So I've got some information here. Accelerates from 0 to 28 meters per second in 11.8 seconds. There's your mass, your CO2 emissions, your fuel economy. Let's have a look what's happening for 3 marks. Car uses 10 litres of fuel per week. Calculate the mean mass of CO2 emitted for the car in 52 weeks. So to calculate the CO2 emissions, it's kilogram per kilometres. Well, we need to know how many kilometres it does. The only way to know that is to use your fuel economy. That's why it's worth 3 marks. So I know that it does 31.6 kilometres for every litre. So every litre will give me that. So I use 10 litres per week for 52 weeks. I've done a step there. It should have been 10 times 52. I should have shown that really. So I've gone 520 times, because that's how many litres I've got, times 31.6, because I can get 31.6 for every litre. And that gives me 16,432 kilometres. Now I've got my distance. I know my CO2 emissions is going to give me 8.9 times 10 to the minus 2 for every kilometre. So, because I do this many kilometres, I just times it now by this. And it's going to give me 1462.4 kilograms of CO2. Energy can be lost from cars in a variety of ways, such as inertial losses, rolling resistance losses, and idling losses. State the design features that manufacturers use to reduce each of these energy losses. So because it's picked out 3 there, inertial losses, rolling resistance, and idling. So inertia is just, remember, the ability to remain, to do nothing or to remain constant. So that's just friction, really. Rolling resistance, the same sort of thing. And then idling, when a car is at, I don't know, stopped at the lights and then the engine's ticking over. So let's mention the 3 things. You can reduce idling losses by having a stop-start system. That's where the car just turns off and then it starts back up as soon as you start going. So that's going to reduce the energy loss there. Reduce inertial losses by having low mass materials. So it keeps the mass down. So you can, so if your mass goes down, then you can keep your momentum. And you got this regenerative braking, where some of the energy goes back in. So when you press the brakes, it will use, and the energy will go back into the system. And then you can reduce rolling resistance, which basically friction, by using narrower tyres. And then you can get automatic tyre pressure warning systems. I mean, narrower tyres is fine there. Because when you use narrower tyres, they don't heat up as much. So you're not getting the energy lost as thermal heat then. And yeah, this is definitely going to be a 3-part video. During a journey, the car slows down from 30 to 10. Use equations on page 2 to calculate how much electrical energy is transferred to the battery if the regenerative braking process is at its maximum energy transfer, which is 60%. And these are the bits now where you really need to read that information, because it kind of tells you what's happening. It's at 60%. You're probably thinking, but we've never done electrical energy. Well, this regenerative braking, if only I could say it properly, it turns that kinetic energy into electrical energy. And remember, all energy is the same, whether it's potential energy. It's just transferred from one to the other, and it's all measured in joules. So these equations are interchangeable now. So the kinetic energy from the car, let me just sort this out in a minute and show you which equation I'm using. I'm using KE equals half mv squared there, because I've got a velocity, I've got a mass. I'm just trying to find out the kinetic energy, because the kinetic energy is going to be converted into electrical energy. So let's find out how much electrical energy I got. So I've even done it there. So V is my final velocity, because it's slowing down from 30, which is your initial. Your mass is 1160. Where did I get that from? I got it from the table there. And the time it takes is 1.8 seconds. Not that I need to know all this, because I'm using this equation. The energy is half mv. Well, I need to do it for both to see how much energy gets transferred. So I'll do it at 30 meters per second first. So Ke was 0.5 times 1160, the mass, times my 30 squared, which is my speed there, my initial speed. And that gives me a total of 522,000 joules. And then when I do it at 10 meters per second, it's going to give me 58,000 joules. Okay. Now I need to take one from the other to give me that energy, not lost, but transferred back as electrical energy. So that would usually be at 464,000 joules. But remember, it's 60% efficient. So now 0.6, because 60% is 60 over 100, 0.6. Times 464,000 is going to give me 278,400 joules. Hope that makes sense there, because it's 60%. I mean, that is if it was at 100% efficient, that's the energy that will get converted, because you've got that difference in speeds there. And again, you know, you'd see this and you're already thinking V and U, but we've had to do it for the two to get the difference. And that was difficult, but that was the end of a paper. So the end of a higher paper is always going to be difficult. Another one on rockets here. The diagram shows a space shuttle just after taking off from its launch pad. So you got the total thrust from 5 engines there. And then the total weight is 3 times 10 to the 7 newtons. On takeoff, America's shuttle used 2 booster engines, each providing 12.5 mega newtons. And if we just show you what a mega is, there it is, look. It's times 10 to the power 6. It's going to be 6 zeros after that. And I've written it there. Of thrust along with the shuttle's 3 engines that each provide 1.8 meganewtons. Now it said there it had 5 thrusters, 5 engines. The shuttle and booster maintain a constant thrust for the first 6 minutes, achieving an upward velocity of 27,000 kilometers per hour, which is the same as 7,500 meters per second in this time. Calculate the total thrust of all the engines on takeoff. Well, you've got 2 of these. It says that I've got 2 boosters at 12.5. So I got 2 times 12.5, which is giving me 25 meganewtons. And then I've got 3 of these little ones at 1.8, which is 5.4 meganewtons. And then I've done a calculation there, and it gives me 30.4 meganewtons of thrust. I think that is a very achievable question there for 2 marks. Use an equation from page 2 to answer above the calculation. With your answers, right? With your answers above from the next page, I meant to calculate the initial acceleration at takeoff. Well, we're dealing with acceleration. It's worth 4 marks. So use one equation, but we've turned out we're using more than one equation, I think. So initially I need to calculate the mass of it to be able to get it into FMA. Oh, what have I done there? Oh, I didn't want to do that. Sorry, it's my lumpy fingers. So to get F, I know my force. I know my acceleration from the previous page. I don't know my mass. I need to get my mass. I can do that because I've got the weight and I know gravity. So from this page, my weight is 3 times 10 to the power 7, and gravity is going to be, does it tell me, or do we need to know that? Gravity is always 10, there it is. So 10 newtons kilograms. So we're going to do that calculation to get my mass. I've got a mass of 3 times 10 to the power 6 kilograms. And now I need to get my resultant force. So my resultant force is going to be my weight taken away from that, the big force, which is, let me get my head around this from the other page there. 30.4 meganewtons. Now, to put that into standard form, I would move this decimal one place, so 3.04 times 10 to the power 7. That's where I've got this from. 3 times 10, no I haven't, 3 times 10, got 3.04 times 10 to the power 7 there, minus my weight, which I got from the diagram, which is there. These questions are beasts. To give me 400,000 a difference, so that's my resultant force there going up, which I can also call 4 times 10 to the power 5. And now my acceleration is going to give me force over mass, which is going to give me my resultant force 4 times 10 to the power 5 over my mass, which is 3 times 10 to the power 6, which I've got from there. And that's going to give me an acceleration of 0.133 meters per second squared. Sorry, I think initially I said at the beginning of this question I was looking for mass. I don't quite know. Let's just push on. I don't know. It's a tough old question. Use an equation from page 2 to calculate the mean acceleration over the first 6 minutes. So for mean acceleration, we're not going to use this one again now. We're going to use the speed that it's given us in the previous page over the time it takes. We can get that there, look. So it's got 7,500 meters per second in 6 minutes. So convert your 6 minutes to seconds. That's going to give you 360 seconds. I've done that there. And then you've got your change in velocity, or your velocity, 7,500 is going to give you 20.8 meters per second square is your mean, your average acceleration there. During the first 6 minutes, the rocket produces a constant thrust. Explain why the mean acceleration over the first 6 minutes is much bigger than the initial acceleration. Well, because it dumps a lot of fuel when it's initially accelerating, so you get a mass reduction, and weight reduces, so the resultant force is going to increase, because as the weight goes down, the force is going to increase. The acceleration is proportional to the resultant force, which increases, and it's inversely proportional, so which means that it's going to be a negative correlation there to mass, which decreases, so acceleration increases. And that's that question. So how many have we got to go? 3 pages. Is this a new question? Yes. So let's tidy all this up.